Hey Matt, how are you doing? Good. Those chairs, I can't touch the floor in those chairs, they're too tall. They're super uncomfortable for short people. Up here I stay.
Good. You have your own TV screen.
So
Yeah, I do.
That's true. Last May, graduated, so I'm actually going to postdoc.
Did you want to close to like
Continuing to do physics. I do physics. Not the kind of students do.
Testing, testing. Basically. I'm not going to overcomplicate it.
Yeah, fair enough.
Okay, we're going to go ahead and get started. Hi everyone, thank you for coming. I am Alex Galliano. I'm a postdoc in OIR, and it is my great pleasure to introduce our CFA Colloquium speaker today, Dillon Brout, from not too far away at all. Dillon Brout is, as of last year, an assistant professor at Boston University in the physics and astronomy departments. Previously, he was an Einstein Fellow here at the Center for Astrophysics. He did his PhD at the University of Pennsylvania, and Dillon is an expert in supernova cosmology. He's been very hard at work, despite all of the commitments of being a new professor, working on the Dark Energy Survey, which he will talk about today. We're really excited to have you. So whenever you're ready, Dillon.
Thanks, Alex. Nice to see so many faces. You may recognize my face. As Alex said, I was here, but it was during a pandemic and a newborn, so I wasn't really here. So last time I was here, I had the opportunity to talk to you about Pantheon Plus, which was a compilation of supernovae that we put together for measuring the Hubble constant. And now today, I'm really excited to be telling you about a different supernova sample that we've put together from first light to basically when these papers were released. Finally getting across the finish line was a little over a decade. So a lot of energy by a lot of really awesome scientists. A lot of the work in the Dark Energy Survey is led by early career scientists, so I'll be doing my best to highlight their work, which was incredibly valuable for us. So when it comes to supernovae, the name of the game is put them on the Hubble diagram, or the distance redshift relation. And many of you will be familiar with this plot and the cast of characters that were involved in making this plot, especially Henrietta Leavitt, where this figure, the distance redshift relation, was observed to have a linear relationship indicating that the universe itself is expanding and consequently had a beginning. Perhaps one thing that is often glossed over with this figure that I like to mention is that this data is not so pretty. And even Edwin Hubble was fully aware of this. And so in the paper, he quotes the following: "For such scanty material, so poorly distributed, the results are fairly definite." So he was aware. And yeah, he did get the slope wrong. He's got a slope of 500 instead of what is around 70. Did I lose? Okay. But this is the game we're playing with supernovae, which allows us to see out to much farther distances into the universe, more than 3/4 of the way back to the Big Bang itself. And we use them as standard candles, or really I should say standardizable candles. So we believe they all explode to roughly the same brightness, where we can actually do better than just measuring their peak brightness, which is given by this M term here. We can make additional empirical corrections for what we observe in their light curves. So for example, less luminous supernovae fade faster, more luminous supernovae fade slower. That's typically what's described in this X1 term, and described as the Phillips relationship. We also have a color correction, which is believed to be associated with dust, and we have some other interesting astrophysical corrections. But on an individual supernova basis, we can measure these green parameters, and then from a population level, we can infer what coefficients, and these are empirical coefficients, minimize the scatter in the observed brightnesses, or the standardized brightnesses. Let's see. Okay, so just to give you a little bit of intuition, if we just treated these supernovae like standard candles, just by looking at their peak brightness, we would get a distance redshift relation that looks something like the following, with about 20% scatter. And adding these additional corrections gets us down to about 10% scatter. So you can ignore most of this. We still can measure the expansion of the universe just by looking at their peak brightnesses. But a lot of the game that we're playing when we're trying to do precision cosmology is get it down to 10% or lower scatter, and also model the underlying reasons for that residual scatter, which I'll be talking about. Okay, so we put them on the Hubble diagram, and here I'm showing now the Nobel Prize winning samples from Adam Rees and Saul Perlmutter, and we compare the distances of the supernovae to predictions based on models, cosmological models, where the model distance is given by the integral over the expansion history. The expansion history is governed by the densities of the critical the major components of the universe relative to the critical density, where this parameter here describes the impact of matter and dark matter. Omega lambda is dark energy, where dark energy could be a cosmological constant if W is -1. So one of the parameters I'm going to be talking about is W, the equation of state of dark energy. If that W is -1, then dark energy is this so-called cosmological constant. I'll also be mentioning a parameter called WA, which is just the first derivative of W, looking for perhaps time-varying dark energy. One other thing I'll point out on this slide is that you can see here in the Nobel Prize winning samples, there's basically two clumps. There's a clump at low redshift and a clump at high redshift. And with the dark energy survey, the main goal here with the dark energy survey is to measure lots and lots of supernovae out at high redshift. Designing a survey that does both low redshift and high redshift is quite difficult. That is the goal of something like LSST, but as a precursor to LSST, the dark energy survey has just focused on high redshift, and we combine with existing publicly available low redshift samples. It's really the lever arm that we get on constraining cosmological models comes from the difference between low redshift and high redshift. Okay, so type 1a supernovae largely have driven this really beautiful success story called Lambda CDM, or concordance cosmology. So here I'm showing constraints of the universe where it is not assumed to be flat. The cosmic microwave background here, shown in pink, indicates that the universe is very likely very close to flat. And basically all of these contours for the major cosmological probes intersect at roughly a universe dominated by dark energy around 70%, with about 30% of the energy density of the universe being contributed by dark matter. And so that's why we call it concordance cosmology. But there are a number of open questions, really profound questions about the nature of this dark energy that still remain unanswered. So what is this fundamental cause for cosmic acceleration or dark energy? Is it the cosmological constant or something else? Is it evolving? Is it in fact isotropic and homogeneous? This is the cosmological principle. We, of course, have the Hubble constant crisis, which I talked to many of you about last time I was here. Not the highlight of this talk, although we'll mention it at the end. But this is the idea that basically the end-to-end test of the universe, the expansion rate of the universe as predicted by Planck from the cosmic microwave background, does not line up with the measurement in the local universe today. OK, so in comes the dark energy survey. And this is our data set that I'm talking to you about today. It's 1,635 type 1a supernovae put onto the Hubble diagram. It's the largest high redshift data set collected from any single telescope. It's really, really incredible. It's essentially doubled all available supernovae over the last 30 years within the 5-year time span of the dark energy survey. And I guess one of the interesting statistics is that roughly 80% of all known asterisk, meaning cosmologically, oh, that should say viable, not variable, viable. Cosmologically viable high redshift supernovae are from this sample. So basically, there are lots of type 1a supernovae out at redshift 2 for which we have one data point, but we can't measure cosmology from that. So 80% of all the supernovae above redshift 1 that are being used currently for cosmological constraints are from our data set. So it's really powerful data set that lets us see basically into a region of parameter space that we haven't really had a chance to look yet. And it's really been made possible by all of these people here and a few more that aren't pictured. But yeah, this was an awesome team to be a part of. So how does our dark energy survey sample compare to the last 30 years of supernovae, which is what I compiled previously in this Pantheon Plus compilation? So you can see here our solid blue contour is what we've done in the dark energy survey. We don't have really any at low redshift. And the orange histogram is the low redshift supernovae that we have chosen to use. So you'll see that as a subset of what is used in the Pantheon analysis. The Pantheon analysis has slightly different goals. The goal is to collect as many supernovae in Pantheon as possible because we want to measure Cepheid variable calibrators. It's a slightly different scientific question we're trying to answer. And whereas with the dark energy survey, we just took the subset for which the systematics are most well-defined and smallest. And that is really going to be the name of the game as we go forward in this talk, is how do we mitigate systematic uncertainties? And so this is one of the main ways that we did that for the low redshift sample. But as you can see, the high redshift sample is just absolutely incredible. Okay, so you might have heard of the dark energy survey in general, and I just want to clarify its scientific goals. It's really got 4 main probes that it is going after, or it was designed for at least. Those being supernovae, weak lensing, baryonic acoustic oscillations, and cluster counting. So I am specifically talking to you about one of these main probes, and you may have heard about the dark energy survey in other contexts with regards to these cosmological probes, and these results are independent of those, and that's also an exciting analysis that's coming up, the combination of all these. So the dark energy survey was carried out on the dark energy camera. It specifically was around 30% of the instrumental time was allocated to the dark energy survey. It's really a community instrument, and you can propose and use it today. Now that the dark energy survey is over, there's lots of time available. It's a 570 megapixel camera with a 2-degree field of view on the Blanco 4-meter telescope in La Serena, Chile. And it was a survey that we carried out for 525 nights over about 5 years. So our mean cadence was 7-night cadence for the Supernova survey. This is one of our images. We have roughly 70 CCDs, and we're able to tile across the southern sky and collect observations of many millions and millions of galaxies. And that tiling was done as part of the wide field survey, so this is affectionately known as the tank. You can see the motivation here. This is stripe 82, and then we avoid things like the LMC and SMC. But this wide field survey is 5,000 square degrees, and that's what is dedicated towards weak lensing and baryonic acoustic oscillations. The Supernova survey is really independent of all of that. It's these 10 fields shown in these circles. It's about 27 square degrees, so much, much smaller area on the sky, where we come back to these regions much more often. And that's what facilitated us discovering type 1a supernovae. We can't really do that in the wide field with only 10 observations over 5 years. So this is our cadence for each of the fields for 1 year. You can see we had really phenomenal cadence, which was influential for our ability to constrain the light curves. These fields are selected. This is one such example of these 3 fields. I think it's this one over here, where they're selected to be in very low Milky Way extinction regions on the sky. This is one of the systematics that we care about, and we'll be caring about a lot more for LSST, because LSST will be indiscriminately surveying that's a much larger area. But we were able to mitigate this in the dark energy survey by just focusing on low extinction regions. We discovered something around 30,000 transients in general using difference imaging, shown here on the left. And of those transients, we think roughly 2,000 of them are type 1a. And we had a follow-up program with OSDES on the AAT, Anglo-Australian telescope. That's maybe some of you are familiar with the instrument 2DF. I think it's a 400 fiber spectrograph with a 2-degree field of view, which is shown in the blue circle. And you can see it's a beautiful match for the dark energy camera as a follow-up instrument. So what we follow up specifically is the host galaxies of the type 1a supernovae. If we're fortunate enough to be following up this region on the sky when the type 1a supernova is going off, of course we get the spectrum of the supernova. But the vast majority of the time, we're just getting the galaxy's redshift that the supernova belong to. Okay, so how do we actually get to the Hubble diagram? Well, it's a little bit more of a circuitous process, and I'm going to walk you through that very briefly. First, we have to model the supernova and host galaxy demographics, and also model potential mismatch between supernovae and their host galaxies.
Water.
Thank you very much. I'm on the tail end of a cold, so hopefully my voice holds out. Okay. We also have to model our survey. how we chose to observe, the cadence, our selection functions, even things like weather and telescope and instrumental effects. We have to, of course, get the redshifts and measure our selection function on getting those redshifts and peculiar velocities. We have to cross-calibrate the filters in our camera, but also we cross-calibrate with other external low redshift samples. We want to know about the relative flux differences between the low redshift and high redshift supernovae and across bands. We care very much about the colors of our supernovae. Once we have calibrated images, we then do a forward modeling process to extract the photometric measurements of the supernovae themselves. And the way that we do that is by both simultaneously modeling the galaxy and the supernova simultaneously, accounting for instrumental effects to get a top of the atmosphere photometry measurement. Once we have those photometric data points, we can then go and standardize those light curves. So the model fits are shown in the lines here. And also with those standardized light curves, well, we also classify whether or not they are in fact a type 1a supernova. And I'll be talking about that.
Sorry, is there a supernova in that movie?
Yeah, there is. And this is a bright one.
Very faint one.
No, this is a bright one.
Right.
If you wait patiently, you'll
Yeah,
see.
I can see it now, but
There. There, yeah. And actually, one of the bright ones are actually arguably more challenging because we're really sensitive to how well we can model the underlying galaxy. Yeah.
you need to model it while contemporaneous. You can't wait, a month later and.
Yeah, so the model is constrained by assuming that there is no supernova flux at some later date. Otherwise, they're fully degenerate. We can't model. But yeah. The challenge and the reason why, one of the reasons why we simultaneously model is because of astrometric issues that happen on a nightly basis. We want to be able to model those at the same time as those same astrometric issues are affecting the galaxy and the supernova. Slightly different. I'm gonna mention that again later.
That's the jitter we're seeing.
Yes.
The jitter of the galaxy.
That I think might just be just pointing.
Okay.
Yeah.
So this hasn't been corrected for astrometry.
The pixels have astrometric solution, but you're always centered on the center pixel. Yeah. Okay. And then once you've standardized, classified, you can then put them on the Hubble diagram, where really what the name of the game is to do is to build a covariance matrix that incorporates all of the uncertainties in each step of this process. So you start in the top left, perturb your analysis by some uncertainty in how you are doing the modeling, and then see how that propagates all the way through, all the way to the end, to the Hubble diagram, and build a covariance matrix that encapsulates your uncertainties. And we validate this covariance matrix, which I'll mention also as well. So the way that we've actually been able to automate this is through a pipeline that we developed within DES called Pippin. And this is really what's turning the crank on doing that whole end-to-end pipeline, because not only do we want to do it once, we want to do it thousands of times, maybe even millions of times for simulations, and we want to do it all in the same way we treat the real data and the simulations. We want to automate it all. And so now it's a asynchronous, fully parallelized, really phenomenal code, really mostly written by Sam Hinton, and is now being heavily used in LSST Desk and also NASA Roman Pit. Okay, so what have we focused most of our effort on? And that is systematic errors. So the joint light curve analysis, which is a similar effort that culminated in 2014, had systematic errors that were 60% larger than their statistical errors. So back in 2014, it was already thought that we were butting up against the systematic floor. Then in 2018, along comes Pantheon and our preliminary dark energy survey analysis with a very small subset of our data set, in which the systematic errors were basically roughly equal to our statistical errors. And that is perhaps not a coincidence. It's basically, we've done every effort we can to push down our systematic errors and understand what's causing them from independent data sets and also from our own data set itself. And basically, it's perhaps not a surprise that more recent analyses have roughly equal systematic and statistical errors because it's a lot of effort to push down your systematic uncertainties, and really once you've hit the same level of your statistical uncertainties, you don't get as much bang for your buck in putting in that effort. So I don't think this is a coincidence. But I'm going to talk to you about a lot of the effort that we've put in since 2018 to push down the systematic floor because we know that our statistical floor is going down with this massive data set. Back in 2018, with our preliminary analysis that had roughly equivalent systematic and statistical errors, we identified really 3 key areas that were limiting our systematic errors, those being our ability to simulate the DES supernova sample from first principles. Number 2, modeling of the astrophysics of Milky Way and host galaxy dust and supernova progenitor physics. And number 3, the calibration of DCAM, of course. That's what everyone always worries about and is certainly something that we worry about as a supernova cosmologist. So that was for the Dark Energy Survey 3-year analysis, the preliminary analysis. And going forward, we also had 2 additional challenges coming from the fact that now when we go to a much larger sample, we actually require machine learning to identify which supernovae are, in fact, type 1a. So we have to model our ability to accomplish that machine learning successfully. And also, because we don't have a spectrum of the supernova itself for every supernova, there is a possibility that we could misassociate the supernova and its host just by using an image. Okay, so we've written now, at this point, over 3 dozen papers leading up to this result, and many of them are pushing down this systematic floor. And I'm going to try to rapid fire go through just a few of these to give you, I hope, build some confidence in our result and the effort that we put in. So as I said, we do this forward modeling approach to perform the photometric measurements. This is called scene modeling. And we get out a model for the galaxy and the supernova itself with some assumption of the PSF of the instrument and the throughput, and atmospheric modeling, and we get out top of the atmosphere model for the supernova and galaxy. Okay, so really, since 2018, though, we've taken this to the next level. So now, with the help of Jason Lee and Maria Acevedo, we are accounting for effects that really haven't been accounted for in any previous supernova cosmology analysis, like effects like DCR, differential chromatic refraction, the fact that the positions of stars and supernovae and galaxies tend to shift ever so slightly on the sky depending on their source color and how it interacts with the atmosphere, and then seeing a very similar effect, but this really changes the size of your PSF as a function of the source color. This is obviously exaggerated in simulations, but Jason and Maria have put these simulations through into our forward modeling framework, and it is now accounted for. We have pushed very much so on the calibration of the images, but also of the SALT-3 light curve model that we use to model the type 1a supernovae. So SALT-3 is this model developed by Darcy Kenworthy. This is not a DES effort. This is a supernova-wide effort to have the best possible model for a type 1a supernova spectrum over time. What I'm showing here is basically a ratio of the peak spectrum, the spectrum at the peak for different systematic uncertainties that propagate into our analysis. Mainly, the thing that we've investigated is how systematics, due to calibration, affect the inference of the SALT-3 surface, spectral surface. So we've improved the data set for SALT-3. It's now 1.5 times larger. Most importantly, it goes both rest frame bluer and redder. And we're motivated to do that on both ends of the model because DES has, of course, lots of high redshift data where we're looking in the rest frame UV. And we also have really sensitive, deep depleted CCDs compared to something like the Supernova Legacy Survey. So at low or moderate redshifts, we care much more about getting the most out of the information on the red side. And perhaps the most important part of this effort was to propagate all these calibration-related systematic uncertainties. So how well all of the supernovae that went into the training of the model were calibrated, how that propagates through the derivation of the model itself also had not been done simultaneously with light curve model fitting. So we have a process in which the model and the fitting are perturbed simultaneously, and this actually has a large impact on our calibration systematic uncertainties and is something that we're going to have to improve drastically for LSST going forward. So LSST, certainly in year 1, won't have an improved training data set of SALT3, and so we're going to have to try to improve upon the calibration of the data sets that go into the training. We've also done a deep dive on host galaxy misassociations. This is a new problem that we have when we have a photometrically classified sample without supernova spectra. And so as you can see here, this is what we call a high host confusion scenario. The calculation that we make is called the DDLR, or DLR standing for directional light radius, and D standing for basically derivative of that. Basically, what you can see here is that a supernova that may be farther, if you just looked at like the angular separation between this supernova and this large galaxy, you would find that it has a larger angular separation from this galaxy and a smaller angular separation from this smaller galaxy. But we know, based on the fact that we can observe the light profile of the galaxy, that it is much more likely, and the direction of the light profile of the galaxy, that it is from this supernova is hosted by this larger galaxy, even though it has a larger angular separation to it. So this is work that Helen Koo has led to model our ability to make these associations. She builds an 8 million host galaxy data set from our catalogs, and also applies various observational selection effects, and attempts to model in simulations of supernova samples based on Sersic profiles measured from the data set, where and how often you would get a mis-associated supernova host. And what she's modeling here is basically the most likely host and the second most likely host. And the data points, the points are what we actually observe in the data. She gets, among many other parameters, agreement between these simulations and data, but also attempts to change all of these different aspects of how she does the simulations, how she scales the Sersic profiles, how she selects the galaxy catalog, how the supernova classification is performed, which actually, because the classifiers often utilize redshift information, this could change how supernova classification performs. And what she finds is a change in the equation of state of dark energy that is quite small, and ultimately this host mismatch effect ends up being about or less than 10% of our total error budget on cosmological parameters. Okay, so I mentioned classification. Let me do a quick dive on classification. As you can see here in our Hubble diagram, there's a number of points that sort of lie off and kind of look like outliers. Those are also often having low probability, light blue colored data points. That's the probability of being a type 1a supernova coming from machine learning classifiers. So the real key challenges that we've had to face is how do we reliably train these classifiers, robustly train them, not overtrain them, and account for unforeseen potential in real data sets, and how do we assess biases on cosmology from how well these classifiers do. Okay, so again, this is also led by Helen Koo and Anais Moeller and Yves Kovacs. We've developed 3 in-house machine learning classifier based on supernova light curves. The main motivation is that we just can't get real-time spectra of 2,000 supernovae. So there's really 2 key points that come out of all this work. Number one, that the classifiers do really well. 98% purity and efficiency, basically, on a high redshift sample. That's largely because we're just doing binary classification, and I've asked people like, Ashley, please tell us if we need to focus on this more, because we're seeing really incredible numbers. It's kind of hard to believe, but the answer mostly I've gotten from the machine learning classification community is for binary classification of type 1As, where we know the intrinsic spectrum quite well, and we can model that in our simulations of the photometric data set, this is not unreasonable. And ultimately, even if you had lower probabilities, it wouldn't really matter as long as those probabilities are well calibrated. So our cosmological likelihood incorporates those probabilities, and the probability of where a supernova, if it was misclassified, would end up on the Hubble diagram based on what alternative type it could be, a 1bc, type 2, whatever it may be. We have also characterized those distributions, and we can get unbiased cosmology out, even with a non-perfect classifier. This is kind of showing you the brute force approach that we've gone through to justify that for ourselves. This is really important work led by Maria Vincenzi. And what she does is she changes the underlying model of classification. So basically what templates or what supernovae go into training the model. And also what assumptions you're making in the data set, basically what kind of dust model you're using and so on, and all the different possible combinations of them. So you can train and you can fit on different combinations and see what's your worst case scenario for, if I trained on a data set that was not representative of the data set that I'm fitting on, how wrong could you be? And these numbers are all quite small. They're on the order of 1 to 2% purity differences. So all very small differences in the output data set that you get from these classifiers. And this is really a testament to how well we understand the spectrum of a type 1a supernova. And basically at this point, Maria says systematic uncertainties associated with contamination are estimated to be at most 0.4%, which is just, we're in the realm of 10% when we're going to measure dark energy. So just basically for the foreseeable future, this is a solved problem. We've also spent a lot of effort to improve our modeling of the intrinsic variations of type 1a supernovae. We, as I said, can standardize these type 1a supernovae down to about 10% variability, and then that's a floor in which we don't really understand why they vary beyond that level. So there's some 10% scatter, and what we try to do is come up with a model, a population-based model for how that scatter could be. And that model can actually be constrained from the data itself, but not on a supernova by supernova basis. So only from the population as a whole. And we do that first by looking at a model based on dust. This dust model does claim to be able to explain the vast majority of that remaining scatter in the Hubble diagram. This dust model has a dependence on color, not unsurprisingly, and also has a dependence on the host galaxy properties. So we look at a number of different properties. I'm showing here high versus low mass, but we also look at star formation rate, age, host color, a number of different things to determine how well we can constrain the dust population from which the supernovae are drawn from, or the lines of sight through which we get to see type 1a supernova through dust. There's also much effort in the supernova community on modeling supernova progenitor scenarios. We do this in simulations as well. The progenitor scenarios are expected to impact the supernova stretch parameter here. So now I'm showing you the data versus simulation, compared to simulations for two populations, old versus young progenitors, and how that we would expect that to impact the supernova light curve stretch, or the time duration of the light curve. And we include this model in our analysis. But really, ultimately, the main conclusion that we find is that the data are better reproduced by following recent work implementing a step in total to selective dust extinction ratio. So we find that this is a better representation of what we see in the data, but we still include this as sort of a systematic uncertainty because it's a hot area of study in the supernova community. Okay. We have also spent a great deal of effort to validate our analysis methodology. And that comes in 3 flavors. The first one is to validate our statistical uncertainties. This is effort led by Patrick Armstrong, where essentially we brute force validated the Niemann confidence interval, not just at the center of our statistical contour, but at the edges of our statistical contour. So in fact, a 1 sigma error bar really does mean a 1 sigma error bar in this really funky kind of banana contour that we're putting out as our main cosmological result. What we say is that at the extremes of the banana, it's about 3% agreement between a brute force approach in simulations and what we do in our main analysis on the real data. When we're doing the analysis on the real data, we use simulations of our data set. In those simulations, we need to assume some cosmological model, and that opens, of course, up the opportunity for bias based on the assumed cosmological model that we have in those simulations. And Ryan Camilleri has been leading work that will be published shortly, showing the procedure by which we can ensure that there is no cosmological model dependence that we have followed in the dark energy survey. And it boils down to the fact that as long as your simulation of your sample falls somewhere along the degeneracy direction of the cosmological parameters, as long as you choose your simulation to be somewhere along this line, then you're okay. You don't get out biased cosmology. So basically, all you need to do is pick some random cosmology out here for your simulations, do your cosmological analysis, find what best fit cosmology you get from your real data, and then resimulate one more time. It's a process. It's a closed loop. It's not an infinite loop of reiterating. You only have to do this once, and that's the proof that he shows in this paper. And lastly, back with the previous analysis, we also tested the linearity of the assumption of linearity in our systematic uncertainties, where we, when we build a covariance matrix, we also can, instead of building the covariance matrix, simulate hundreds of times our data set with linearly independent systematics, and see how our reported uncertainty using a covariance matrix compares to a forward modeling approach of all the different individual systematic uncertainties and then how they interact with each other. And what we find is that it is a good representation of our reported systematic uncertainties. Okay, I have time to do this. This is a fun one that I am personally passionate about, which is called binning is sinning. So this is a paper that I wrote actually back in my time here. That comes in a line of other papers with similar titles and actually motivated by these papers. So a paper by David Kipping called Binning is Sinning. David Hogg tweeted about that. If binning is sinning, then stacking is hacking, and then wrote a paper with Kate Story-Fisher on large-scale structure stacking. And so our version is Binning is Sinning Supernova version. And how if you bin your data set, you're losing information, and we should not do that. So the Dark Energy Survey 3-year analysis, that's what we had from back in 2018, did bin our data set. So you can see here, these are all of our systematic uncertainties and how they compare to our nominal analysis. And in order to make this computationally feasible, we binned them up. The joint light curve analysis from 2014 also had this, they were sinners, and so was actually the Rubin LSST science requirements document. Did this as well. Now, I should say, it was done motivated by the computational infeasibility, and so one of the efforts that we made in this paper is to overcome that, and I won't get into the details of that, but now that we've overcome and we're able to not bin our systematics when analyzing our covariance matrix, we can take advantage of the following. So imagine some systematic uncertainty. This is our y-axis, our difference in distance or difference in observed magnitude compared to a nominal analysis. So you don't even have to know what the systematic is. All I can tell you is our distances change if I do perturb my analysis by some systematic, and I'm going to plot it as a function of the supernova color. So you can see here there's this really interesting structure that this systematic uncertainty is doing, okay? And if I bin this diagram, I get this. So this is the difference in distance, but now binned as a function of redshift. And this is what we had been doing in the field up until very recently. And what you'll find is that you lose a lot of this beautiful information and you get a curve as a function of redshift, which could look a lot like your curve for your different cosmological model. But we know that dark energy doesn't make supernova light curve colors at this color change, but this color not change. This is not dark energy, but this could be. So we want to make sure we preserve this information. Okay, so just to kind of illustrate this, we showed using an approach by Faccioli that you can constrain both your systematic uncertainty, capital S. So if you have some knowledge of how your systematic changes your observed distribution, you can constrain a variable capital S, and you can constrain your cosmological parameters simultaneously. So that's what's being shown here. Capital S, omega matter, and W all constrained simultaneously. And what you see here is that if I bin my analysis, I get a really poor constraint, the black dashed contour, on capital S. But if I don't bin my analysis, I can constrain, because I know how capital S behaves and it's not binned, I can constrain it down to size basically of the blue contour, which results in a correspondingly smaller contour in your cosmological parameters. If your systematic, so on the left-hand side here, I was showing you a systematic that has a color dependence like the one I just showed you on the previous slide. But if your systematic does not have any color dependence or have any other dependence other than redshift, if your systematic only changes things in redshift, you really don't get this benefit. So you're just kind of screwed. But that being said, a lot, if not most, of our systematics in supernova cosmology have some other dependence like color or stretch or something else. And so that's really exciting, because just from not binning our data set, now DES has been able to reduce the error budget by a factor of about 50%. And it gets better, because the kicker is that this effect improves as your data set grows. You can constrain down the size of certain systematic uncertainties that have some non-redshift dependence. As your data set grows, the systematic itself will just get smaller. And that's really exciting for future surveys like Rubin and Roman. Okay, so in light of all of this, what now is driving our error budget? Well, okay, don't let your eyes glaze over. I'm going to summarize this really briefly. The first thing to look at here is that this left-hand column is the statistical error that we get for dark energy survey, and the right-hand column is the systematic error. So we are not dominated by systematic errors anymore, which is really exciting. Number one, our systematic associated with classification is the smallest systematic. This is not a coincidence. There's a lot of effort that's gone into improving machine learning methods over the last 5 years. The field has moved extremely rapidly, and it is just not a limiting factor for us anymore. And our top systematics really reside in the area of understanding supernova dust and astrophysics, and of course calibration, where I'm talking specifically about both in the training of the model and in the fitting of the DES light curves. So this is really the critical path for LSST and what we're focusing on going forward. Myself and Maria Vincenzi are leading the LSST desk time domain working group as we speak. Okay, so for cosmology, you've all waited very patiently. Thank you. So the left-hand plot is flat Lambda CDM. This is a one-parameter fit. Measurement of the matter density. And from the DES supernova alone, we get 0.35 plus or minus 0.017. And that's basically on par with the constraint that Planck gives for flat Lambda CDM, which is really impressive. I'm showing here our result in the blue teal. And then we also, in a number of these results, also combine with the publicly available data sets for the CMB, BAO, and the DES 3x2-point weak lensing analysis. we are consistent with the Planck omega matter. I think the Planck omega matter sits roughly around 0.31 plus or minus 0.02, so within 2 sigma. When it comes to open or curvature allowed lambda CDM, this is our contour. We get omega matter of 0.29 and curvature consistent with 0. And again, this is basically our new version of the concordance cosmology figure. Now, when it comes to measuring the equation of state of dark energy, W, you can see our blue contour. We get W of minus 0.8, and it's a little bit over 1 sigma from W of minus 1, or the cosmological constant. Nothing to say there. And even when we combine with other publicly available analyses, we get that it is consistent with the cosmological constant, albeit slightly preferring a larger value of W, but still not at any level where we would begin to claim anything. Now, lastly, we examine our constraints on time-varying dark energy. So that's this equation, that's this parameter WA. You can see here these contours are relatively zoomed out because our contour on WA is rather large. We get really the best constraints on WA by combining with other samples. And really, at the moment, in the current generation of surveys, this is not unique to DES. Nobody can really measure WA very well. Any conclusions that we're making about WA at the moment are coming from combining the different samples and different probes. And again, we find something that is roughly 2 sigma from a WA of 0, which would imply no time variation of dark energy. It is interesting that a number of the different probes are pointing towards lower or negative values of WA. There is no, this preference for 2 sigma below 0 is not driven by any one probe. They all sort of have a slight preference for slightly negative WA, but again, not statistically significant at this point, but really exciting for us to keep pushing forwards. This WA less than 0 would indicate that dark energy equation of state is increasing with time, or that the universe is what we call thawing. Okay, so a couple of the big questions maybe I can preempt. Is the universe accelerating? Yes. Dark energy deceleration parameter, Q0, so this is what was originally measured back with the Nobel Prize winning samples. It's just a sort of a parameterization that can be described as omega matter over 2 minus omega lambda, but it's also described as perhaps interestingly as the deceleration parameter. It's negative. The universe is accelerating at over 5 sigma just from our data set alone. Is dark energy a cosmological constant? Well, what we find is that it is consistent with W of minus 1 at minus 2 sigma. If you combine all of these data sets and if you look at them all individually, there's a mild preference for negative WA, but nothing to say. And then lastly, one that I'm expecting to get, and maybe I'll just answer right now, do we resolve the Hubble tension? Okay, so no. Sorry. The DES supernova are uncalibrated in the sense that they have not been calibrated to an absolute distance scale. This is the reason that we do the cosmological distance ladder and tie them to Cepheids and geometric measurements. We cannot do that with the DES sample. It does not go to low enough redshift to do that. So we cannot measure H0, which is, in our analysis, degenerate with the intrinsic magnitude of a type 1a supernova. You could potentially ease the tension by having a W that's greater than minus 1, but we don't see that tension easing with this parameterization. We cannot directly measure H0, But I will say that we do broadly confirm a number of the underlying supernova and dust models that were used in the SHOES or H0 measurement. And this is an independent sample that has been able to independently confirm the modeling choices that were made in that analysis. Okay, so we're all now largely looking forward to what's coming next. I think I just saw a video of the LSST mirror going to its final resting place. From the supernova perspective, as you probably know, LSST is just absolutely incredible. So just to give you a little bit of comparison, the dark energy survey weak lensing analysis was 5,000 square degrees on the sky. As we saw, that's the tank, 5,000 square degrees, and LSST will be about 18,000 square degrees. It'll go to a little bit higher redshift, but it's basically, a factor of 3, times, and then volumetric effect. But the supernova survey is going from 30 square degrees to 18,000 square degrees. That is absolutely bonkers, and we're going to have something like 1 million type 1a supernovae, give or take. And so the future of what we're doing here in DES to push down and understand how to analyze these data sets is going to be critically valuable to how we perform going forward. It's like it's like a freight train running at us. It's happening any moment. So with that, I will leave just a quick summary. We have the largest and deepest supernova sample at high redshift, ranging from redshift 0.1 to 1.2. We have made a leap in understanding and treatment of our systematic uncertainties. We do see some hints at interesting physics on the horizon when we combine all of the data sets that are currently available, and that motivates a lot of effort going forwards from the community as a whole. And then we believe that we have shaped the priorities of future surveys and how they're conducted and what people focus their efforts on. So with that, I'll gladly take questions.
Questions for Bill?
Well, this is great. It's great to see all this hard work leading to this. So you had redshifts for your host galaxies, right, from this follow-up program. What are you going to do with 1 million supernovae? I'm assuming you're going to have to rely on photometric redshift. So how does that factor into all of this?
So one thing I didn't mention here is we're working on basically reanalyzing all this with photometric redshifts, just ignoring the spectroscopic redshifts, but using that as a way to confirm that we're doing it correctly. For LSST, there's a number of different approaches that we're working on. We think that we may be able, between DESI and Foremost, get relatively complete spectroscopic host galaxy redshifts out to maybe redshift 0.4, 0.5. And then at that point, we can justify, based on simulations, using photometric redshifts because their impact at those higher redshifts is subdominant to the other systematics that we have at higher redshift and just the overall size of the distance uncertainties that we get at higher redshift. So we think it's going to be a combined approach of spectroscopic at low redshift and photometric beyond redshift 0.5.
Hi, this was great. So looking forward to Roman instead. I'm curious at what volume you're expecting to probe and if you start to really see some evolution in the progenitor systems of the 1As.
Yeah. So for Roman, we think we'll be getting to redshift 3 or 4. When it comes to progenitor scenarios, what we do to understand progenitor scenarios, actually I have a slide. Oh boy.
It's 287.
This one. Yes, okay. Okay, so I guess I can just give you the kind of the basics and then extrapolate to Roman. So the way that we trace evolution of supernova properties is relatively straightforward. This is 95 supernova from 2007. in the very nearby universe, basically redshifts 0.02 to 0.1. So this is the linear regime of the expansion of the universe. So the universe is not it's basically linear expansion. So that means that we should recover a line, and we do. And importantly, within this data set, and this is much larger now at this point, we have supernovae and galaxies that span the full range of light curve parameters that we observe, and host galaxy types, ages, masses, stellar populations. And so within this data set, we have all of the things that could go wrong within here. And we know that at least now it works, and we can trace with external measurements of galaxy properties and tracing the evolution of the supernova light curve properties themselves. If those are changing with time out at higher redshift, we're then tracing the progenitor evolution. Whether or not I'll be able to tell you anything concrete for what's going on in the progenitor scenario, unlikely, but as a systematic that creeps into our analysis, we just want to trace the light curve properties, the ages and the masses, and so on.
So Dillon, I gather you'd have liked to get some measurements down below 0.1 redshift for cross-calibration.
Yeah, of course.
What stopped you in the observations?
You just need to cover a much larger area. You need to, it's one supernova per galaxy per 100 years. You need to cover that, you can do the rates, and you need to cover more, and so you got to, it was a trade-off that we made. I am now running a program on DCAM for the last 3.5 years to take ZTF alerts and Atlas alerts and Assassin alerts that do this broad scanning of the sky at low redshift and follow up DCAM on those low redshift events. So it's not a survey in the sense that we're not discovering anything, but we do get those low redshift supernovae on the DES or the DCAM photometric system, which then we can go and do these kinds of H0 or just minimizing systematic uncertainties due to calibration and address all that. So yeah.
Final questions?
Thanks, Dillon. So given this uniform data set, can you get the rate of type 1 supernovae as a function of redshift?
Yes, we should. So there's a rate paper out there as a function of redshift. I'm not sure we have enough yet, but yeah, I'd be happy to point you to the paper.
All right, let's thank Dillon again. He has an open spot for the next half hour in his schedule if anyone wants to come chat with him.
Hey, this is great.
Good, thanks.
What's the deal with the other 28,000 transients?
Yeah, we're working on a data release.
Okay.
It's all going to come together, the cosmology data release and everything else data
And what's going to be, those are just light curves, right? There's no
difference imaging.